This is May 2013, M1 question number 5, a question on momentum, colliding particles and impulse. So I have started the diagram here for part 1, two particles A and B travelling directly towards each other. So I've got the arrows here pointing towards each other. We know that A on the left has mass 2, speed 4 meters per second. They are colliding. B has mass m, don't know its mass yet, and it's head-on collision, so its direction vector is to the left. So I'm going to be taking everything to the right as positive. It's important that we are sure about which is our positive direction. So in part 1 we're told that the magnitude of the impulse exerted by B on A is 18 newton seconds. That's B on A. So when we come to apply that to the diagram, we have the impulse acting in the opposite direction to the motion. So the impulse is to the left, and that will be important in our diagram because in our equation it's a vector equation, so the direction is vitally important. So we're asked for the velocity of A after the collision, which I'm going to call V, and I'm going to assume that A rebounds and goes back in the opposite direction to it was initially going, so it's going to the left. So I'm going to do impulse is equal to the change in momentum. So I is equal to mv minus mu, the final momentum minus the initial momentum, and this is just for particle A, the 2 kilogram mass. So the impulse will have to be negative. We're told it's 18. That's its magnitude. Mentions magnitude there in the question. That's a bit of a clue. So minus 18 is equal to the mass, which is 2, times the velocity, which will be negative v. So our positive direction's to the right, and we're taking away the mass, 2 times the initial velocity, which is a plus 4. So we get negative 18 is equal to negative 2v minus 8. So solving that equation then, so if we add the 2v onto each side, add the 18 onto each side, we'll get 2v is equal to negative 8 plus 18, which is 10. So therefore v is equal to 5 meters per second. We're asked for the velocity, so we need to specify the direction. So v is equal to 5. Our diagram shows that it's to the left up here, so we're going just to specify that. So because v works out to be 5, the direction that we had here was correct. So that means A does rebound. So it'll be in the opposite direction. Rather, in the opposite direction. And that's the end of part 1. So the next part of the question then says B has mass m, which I'd already put on the diagram. Its speed before the collision is 3. So let's now write 3 before the collision. It was head-on collision, we were told, so therefore it is to the left. After the collision, the speed of B is 1.5. So we don't know what direction it's going in, so it could be left or it could be right, so we're going to have to take both of those situations. So we'll start off, and I'll write it up here, part 2, we'll start off with our first case with the speed 1.5 acting to the right. So 1.5 to the right. So we now are going to use the fact that momentum is conserved. Momentum conserved. I always explain where the equations come from. So that means the total momentum before will be equal to the total momentum afterwards. So if we go to our velocities before along with the masses, that's going to give a total momentum equivalent to what it is afterwards, with our v to the left and our 1.5 to the right. Now I could put the 1.5 to the right on the diagram, and that might help. So let's do that. So the momentum is conserved. So what's the total momentum before the collision? So we have the mass times the velocity of A, and we remember that we've got our positive direction here, our positive direction to the right. So we're going to have 2 times 4, mass times velocity, and we're adding on the momentum of B before the collision, so that will be m, and it'll have to be m times -3, because it's going to the left, which is the negative direction, so that's the total momentum before, and that will have to be equal to the total momentum afterwards. So we worked out in part 1 that V was 5 to the left, so for A then is going to be 2 times -5, and we have assumed that B has also rebounded and it's going 1.5 to the right, so that will be plus 1.5 times m. And we get an equation which we can solve. So therefore we've got 8 minus 3m equals -10 plus 1.5m. So adding the 10 and adding the 3m, we get 18 is equal to 4.5m, and so m is equal to 18 over 4.5, which is 4. So m is 4 kilograms, and that's in the first part. So let's change colour to blue for the other option. So the other alternative is that 1.5 is actually going to the left, so that B keeps on going in the same direction. So for this to happen, we would assume that B would have to be quite heavy, quite a lot heavier than A, because it's going to cause A to rebound, but it'll keep on going in the same direction. Let's see what happens. So again, the initial momentum will be the same, so we can use what we had up here. So we're going to get 8 minus 3m, that was the initial, and the final momentum then will be 2 times -5, so that's still the -10, but B's momentum afterwards will be different, so it's going to be minus 1.5. The 1.5 is going in the negative direction, so minus 1.5 times m. So solving that then, if we add 10 to each side, that gives us 18. We add the 3m to each side, we get 1.5m. So 18 over 1.5 is m, and it does indeed work out to be much bigger than it was before. So there we have our 2 possible values, 12 kilograms if B continues in the same direction, and only 4 kilograms if it was rebounding in the same direction as A. So those are our 2 possible values for m, and that's our question completed. Question 6. First thing we notice is that it says take G as 10 meters per second squared, so I'm going to highlight that so that we don't forget, and it's important that we take G as 10. That's going to make the numbers in the question work out much more easily than otherwise if we were to take 9.8. So figure 2, it says, shows a particle of mass capital M kilograms moving up the line of greatest slope of a rough plane AB. The plane is inclined at an angle of theta to the horizontal, where the sine of theta is 3/5. The coefficient of friction between the particle and the plane is mu. Part 1, draw a diagram and which shows all the forces acting on the particle. So let's draw the plane. This is part 1. Plane, tiny little particle, horizontal, and good idea to draw, I like to draw the mg out of the way. That means I can get my theta in here as well. So theta there and theta there. We have our normal reaction, 90 degrees to the surface. Now we're told that it's moving up the line of greatest slope. So it's moving up. So therefore our friction is going to have to be down the way. So Fr for friction down the plane. Now that's the only information we have. We're not told that there's something pulling it up the plane. We're not told that there's a string pulling it or anybody with a force pushing it or anything like that. We're just told it's moving up the plane. So therefore we must not draw a force up in that direction. There's no information to tell us that there's a force up the plane, so we just have those three forces as marked. So what's probably happening is that the particle has been given a push, being projected from A at the bottom, and then it's just moving upwards. And as we'll see, it'll be slowing down. If you read through the rest of the question, you can see that we have down here, we have that it comes to rest at B. So it is indeed slowing down. So rather than just diving in and putting in another force here, it's always worthwhile just reading through the rest of the question just to double check what further information you have there. You wouldn't be using information from part 2 in order to do part 1, just working with the information above part 1. And there's our diagram. So, part 2. We're told at A, at the bottom of the plane, the particle has a velocity of capital U meters per second. T seconds later, the particle comes to rest at B, and we're asked to find, in terms of mu, the acceleration of the particle up the plane. And then in part 3, show that U is 6 plus 8 mu T. So the time and the initial velocities are going to come in to part 3. But the only thing we want to do in part 2 is find the acceleration. So to do that, we're going to do the normal things. When we have forces, we're going to do our resolving. Now, before we do that, let's just think a little bit about the sine of theta is equal to 3/5. When we're given the angle in that form, again, that's to make the calculations easier, to make the numbers easier. So rather than going to your calculator and working out the angle, what we can do is use the fact that the sine of the angle theta, so here we have it, theta, right angled triangle, the sine of the angle we're told is 3/5. So the opposite over the hypotenuse will be in the ratio of 3 to 5. And from Pythagoras we can get that the adjacent side is 4. So that tells us the cosine of theta then is the adjacent over the hypotenuse 4/5. So we're going to be using 4/5 and the 3/5 in our equations when we resolve. So first of all, and make sure you explain what you're doing, resolving perpendicular to the slope, the normal reaction will be mg cos theta, which is 4/5 mg. So there'll be a marker too for that. And then resolving, I'm going to do up the slope as our positive direction. Okay, so it's moving up, so I'm going to mark on the diagram acceleration up the way. So up is going to be my positive direction. So when we come to look at the forces parallel to the plane, we see that F and the weight, the component of the weight, are both acting downwards, so they're going to have negative coefficients. So it's going to be minus the friction, minus the component of the weight, which is mg sine theta. And that's it. Those are the only two down the plane, and that will be equal to the mass m times the acceleration we're trying to work out. So thirdly then, and we'll put in the sine theta afterwards, thirdly we're told that the coefficient of friction is equal to mu, so the friction is equal to mu times r. And if we bring in r from this first equation, we're going to get the friction is 4/5 mg times mu. So there's our friction. So if we sub that into the equation just above it, we'll have minus the friction, so minus 4/5 mg mu minus mg times sine theta, which is 3/5, and that will be equal to the mass m times the acceleration. And we have all the things that we need in this equation. Now, if you look closely, you'll see that m is appearing as a factor in every term. So we have 1, 2, 3 terms. So we can divide the right-hand side and the left-hand side by m. We also know that g is equal to 10. Now, I could have gone back. If we go back and put 10 in at this stage, didn't, so we can put it in now. So minus 4/5 of 10 is going to be minus 8 mu. and then minus 10 times 3/5. 10 times 3/5 will be 6, and that will be equal to A. And that's what we're asked for. We have A in terms of mu. So there's 8 marks altogether for part 2. So there's a lot of work in there, a lot of thinking in terms of the angles that we had up here, in terms of resolving perpendicular and parallel to the slope. And I'm noticing that I should have put in F equals MA. So I can go back now that I'm checking and write in the equation, F equals MA. And then we've also used F equals mu r. So 3 equations there with lots of calculations as well for the 8 marks. So for part 3 then, I'm going to just come across to the left-hand side of the page, part 3. And we're asked to show that u is equal to 6 plus 8 mu times t. So if we go back to the information we have here, we have at A, where the particle started, the initial velocity then was capital U. We're told that t seconds later it comes to rest at B, so v is equal to 0 when the time is t. And we've also worked out the acceleration, so we also know that A is minus 8 mu minus 6. So if we use then v equals u plus at, we're not asked to work out anything, we're just asked to show this relationship between u and mu and t. So subbing these 4 things in, we'll get v, which is 0, is u plus capital T times A minus 8 mu minus 6. So if we leave u where it is, and this term then, taking it over to the other side, we'll have t, so that'll be, these will become plus then, so it'll be t times 8 mu plus 6, which is equal to u. And there we have it in a slightly different format from that given in the question. So if you really want, you could write it at the end as it's given. So u is equal to bracket 6 plus 8 mu. So just rearranging the order here and then putting the t at the end. And there's the 3 marks. So 13 marks altogether. Now just going back over some of the important things in the question. So we've said already the g is 10. Moving up the plane and no force in the upward direction. No information which tells us there's that force, so nothing up there. Using our 3/5 and 4/5 and being very careful with the direction here with these minuses, making clear that positive is up the plane, and then just being careful with the algebra as you're working through here and in part 3 as well.